Lesson 2-13. What are we doing today? We are solving. We're done with properties. We've been going through properties. We've been doing key features, things like that. Today, we are solving exponential and logarithmic equations and inequalities. But today, we are focusing on solving the problems. We will apply the things we've learned, but we will solve today. So before we begin, on this second slide in your packet, I wrote down something that's very important for you to know, and that is the properties that we have been learning about. You have to know your properties. So how many properties did we have for exponentials? Say three. Three. And how many properties do we have for logarithms? Three. Plus, there's one more that's actually on here. There is a change of base property. I'll go ahead and list that at the bottom. Change of base. So the change of base property looks like this. If you have a log, I'm going to call it a base of b of c, log base b of c, you can solve that by taking the log of any base whatsoever. I'm just going to leave it as a common log. Log of c, so say common log of c, and dividing that by log of the base, like this. Mathematically, this is the same. Now, technically, you could choose any base, so I'll put an n down here, where n, the thing is about n, the base has to be positive, so n has to be greater than 0, and it cannot be 1. Okay, as long as that's true, as long as n is positive and not equal to 1, you could choose any base whatsoever you want to do. You could choose pi, you could choose e, but I would just use common log, log base 10 of c divided by log base 10 of b. That's how I would do it. That's one more property that's not on there. And this is a review of how to convert between the two forms, how to perform the inverse. Just look back at this if you need to, okay? The next slide is going to be the steps I use throughout the lesson to solve if there's one logarithm. Okay, I'm going to fill in their blank here, and then after that, I'm not going to go back to this slide. This is for you as a reference. Okay, I'm going to walk you through step by step how we do this. So the thing we're going to do is first isolate whether it's an exponential or log that we're trying to solve. And then to solve the problem, and this is if there's only one logarithm or exponential, we will apply the inverse. Inverse is your blank. We're going to apply the inverse to convert it to the alternate form. From there, we will solve for the variable, and then we will simplify or round if we need to. Oftentimes, step 3 is not necessary. So a lot of times we'll go step 1, step 2, and then jump to step 4. But you'll see some problems where step 3 comes up. But like I said, this is just for reference. Just look back at this later if you need help on solving the problems if you don't catch it in class. So let's actually begin on our problems. The next slide, example 1. Problem A. For each of the following, what we want to do is write an equivalent equation by condensing each equation to a single logarithmic equation and then solving for x by applying the inverse. It doesn't say that there, but that's what we're going to have to do. So let's look at the first problem. The way to solve either anything that's exponential or logarithmic is to isolate the exponential, in this case, or the logarithm, if you had the word log. Okay, so how would I isolate this? 4 to the power of x. I agree. We're going to add 2 to both sides. So we add 2 to both sides. We're left with 4 to the power of x equals 9. Now, once you have it isolated like this, we can apply the inverse to solve. Let me go ahead and drop that. So 4 to what power equals 9? We don't know. So we can convert it to, what's the inverse of exponential? Log. If I convert it to a log, I can solve this. Now remember, with the log, when you apply the inverse, what happens is these two switch places with each other. When I do the inverse, these two will switch. So the base stays, it's log base 4, but I don't raise it to the x anymore. What do I now make it look like it's raised to? 9, and that equals x. Now that's our exact answer right there. We applied the inverse. That's the exact answer. I have nothing else I have to solve. So this is one where I would skip step 3. But step 4, this says to approximate. We want to approximate by rounding to the nearest thousandth. So I'm not going to leave my answer in this form. We're going to approximate, which means I'm going to do X with a squiggly. Let's go see what this is in the calculator. So open up your Inspire. And we will calculate this. Control log is on the left side of your calculator. Base 4 of 9, press enter. And in case, for whatever reason, you did not have a Inspire, maybe you're using a cell phone and it's not up to date. Maybe you have an old calculator you want to use. You could also do the change of base. Remember what I said that is? You take the log with any base. I'm just going to leave the base empty, and you would divide that by the log of what was the original base. What's my original base? 4. And like magic, you press enter, and what can you tell me about the answer?
1.584.
It's the same. Now we need to round this. It says nearest thousandth. 1,000 had 3 zeros, so we need 3 decimals. So we're gonna have to round that answer, but that's where we're gonna get our answer from. There. And so 1.584 or 1.585. 1.585. That's going to be our value. I'm going to say 1.585. 1.585. That's going to be our solution to the first problem. And now we're going to reload and do this all over again. Let's take a look at number 2. Number 2, Ruby, what would you do first to try to solve number 2? Ruby. Thanks for joining us. All right, what would you do first? You want to get this isolated right here. So how do you get rid of a plus 5? Subtract 5, that's the inverse operation. So let's subtract 5 from both sides. That's the opposite. So 2 to the power of x plus 3 will equal 21. Now we have the exponential isolated. That was step 1 that we just accomplished there in red. So step 2 is you convert it to its inverse. Now what's the inverse of an exponential?
Log 2.
A log. Now again, when we do an inverse, these two items are going to switch places. So it's now going to be log with the base of 2 raised to the 21st equals x plus 3. Now, before I go to the calculator, I'm going to do, this one has a step 3. Step 3 says to solve for your variable if necessary. I still haven't gotten x isolated. What can I do here to get x isolated? Subtract 3. Now, pay attention, or be careful. I should say be careful here, not pay attention. Hopefully you are paying attention. When I subtract this 3, am I subtracting from a logarithm on the right side? No. So don't subtract from the logarithm here. Don't say 21 minus 3. Just put the 3 on the outside. So it's now going to look like this. Log base 2. And just to make sure we don't make a mistake, I'm going to put a parentheses around the 21. That does not get subtracted. What does get subtracted is the logarithm entirely. It's kind of like a vertical translation, to use transformation terminology. That's on the outside, not on the inside. I'm not doing a horizontal transformation. I'm doing a vertical translation of minus 3. Now that's our exact answer. Let's go approximate this. So let's go to our calculator and see what this is when we round it to the nearest thousandth. So log 2 of 21 minus 3 on the outside. What's another way you could have typed in log 2 of 21? Log 21 divided by log 2. You could do it either way. And there's our values. Okay, so when we approximate this one, 1.39, will it be a 2 or a 3? 2. And that's our second solution. So these are just the steps of how to solve algebraically with logarithms or exponentials. Now, part C, all I try to do is throw in a little bit more complexity. Now, I don't want you to get confused here. Can I combine this 3 minus 4 over here? Why not? This -4 is a coefficient. It's connected to the e to the x. These are not combining like terms. These are not like terms. That 3 is all alone. The -4 comes with e to the power of x. So I cannot combine those. Yeah. Come on now. So I can't do that. So what can I do with this 3? We could subtract this 3 from both sides. I can do that. The inverse operation of a +3 is a -3. So those will subtract. What is -7 minus 3 more? -10 will equal -4 times e to the power of x. I still can't do step 2 yet. I cannot move to the inverse because I still haven't isolated this base. How do I get rid of this -4 that's multiplying?
Log.
I can't do log yet. I need to get rid of the -4. And so since -4 is multiplying, the inverse operation is to divide by -4. That is the opposite. We will divide by -4. What happens when you have a negative divided by a negative? Positive. And I'll reduce this. What number goes into both 10 and 4? 2. 2 goes into 10 5 times. 2 goes into 4 twice. I reduce that by a factor of 2. I've divided out a 2 from the numerator and denominator. So 5/2 equals e to the power of x. Now we've isolated our exponential. So now I can move to step 2, which is to apply the inverse operation. The inverse of an exponential is a log. What's my base this time? E. Now when I apply the inverse, these two switch. So it's no longer e raised to the x. It's now e looking like it's raised to the 5/2. And that will equal x. Now there's a better way of writing log e. So what I want you to type in is the natural log of 5/2. And we will round this again to the nearest thousandth to see what we come up with. So the natural log of 5/2. And I will prove to you that that is the same thing as log e to the 5/2. So you know what? I'm not sure if I can do this. I want to try to see if I can delete the power entirely. Nice. Let's see if this works. Yes, it does. Again, we want 3 decimal places. So will we leave it as 9.916 or will we become 917? Still 916. All right, good. (0.916). All right, there's our solution there. And so I'll let you now begin working on your DOL. DOL number 1. All right, now let's go look at solving logarithms. So you just saw solving exponentials. Now let's try solving logarithms. It's the same process. So looking at this logarithm here, what should we do first to solve this logarithm? What would you think we should do first? Let's subtract the 4. Very good. What we're going to try to do is isolate the log. Instead of isolating a base like exponential, we're going to isolate the log. So now I have 2 log base 3 of x plus 3 equals 6. I didn't read this, by the way. I'm sorry. But it's telling you to condense this equation into a single isolated logarithm and then apply the inverse to solve for x. Okay, I'll let you think for a moment. What do you think we could do now? Now there's 2 options. Number 1 is you could do power property, which means this 2 can do what? but that doesn't simplify anything. There's another thing we could do that would actually simplify and get rid of the 2 permanently. What's the 2 doing to the logarithm? Multiplying. Since I'm actually can solve this equation, there's another way of getting rid of multiplication. Division. And that's what I choose here because it simplifies the problem. It condenses the problem, if you will. So that cancels out. Could you make it a power? Yes. And you could still solve it that way. It's just later we'll have to deal with that 2. This way we get rid of the 2 permanently. 6 divided by 2 is 3. Okay. Though we did 2 steps, that would fall under step number 1 on that slide, your little step on the steps of how to do it. Step 2 says to apply the inverse to solve the, whether it's an exponential or logarithm. What's the inverse of a logarithm? Exponential. So you ask yourself, what's the base? Let me draw an arrow. The base is 3, so it'll be this 3 raised to the power of, instead of x plus 3, we do the inverse. And so when we do the inverse, what happens to these 2 values? Switch. So it'll be 3 cubed equals x plus 3. I don't need that parenthesis anymore. Parentheses typically means multiply. There's nothing to multiply with, so the parentheses can be dropped. Do we need to use a calculator, or do you know what 3 cubed is? 3 times 3 times 3. It is 27. Good. So this will be 27 equals x plus 3. Which brings us to our final step. We subtract 3. This is step 3. This one we still need to solve for the variable. That would be step 3, which says if necessary. Step 4 is to simplify. There's no simplification, so this time step 4 is not necessary. Whoops, I wrote 30. That's bad math. What's 27 minus 3? 24. That equals x. That is our solution there. 24 equals x. That is our solution right there. 24 is x. Whoops. Y'all ready to reload and try again? Okay. How do I solve this logarithmic equation? Why are we subtracting 2?
Because it's not multiplying.
We want to isolate the logarithm. This 2 is adding. The inverse operation is to subtract. So if I subtract by 2, that gets simplified out of there. It's canceled, if you will. Log base 5 at 2x minus 1 equals 2. That was step 1 from that little cheat sheet I gave you. We're done isolating the log. So what is step 2? Inverse. When you take an inverse, these 2 values of a logarithm, I should say, these 2 are going to switch as part of the inverse. What is my base? Instead of being 5 raised to the 2x minus 1, now it's going to be 5 raised to the power of 2 equals 2x minus 1. 5 squared. 5 squared is, so 25 equals 2x minus 1. Now we're on step 3. We're going to isolate this variable, which means we add 1. 25 plus 1 is 26. That equals 2x. And finally, the last step here is we need to perform the inverse operation to get x isolated. What is the inverse of multiplying by 2? Divide by 2. That is the opposite operation, the inverse operation. So now we can state confidently that x is equal to 13. Good job. No rounding necessary. Okay, we're going to do this one more time before I ask you to do it. All right, what about part C? Good. What is that 5 doing to the natural log? That's not IN, that's an LN. I like Ellen DeGeneres. It's a natural log. It's dividing. What's the opposite of division? Multiplication. So we multiply both sides by 5. And now I have the natural log isolated. It's natural log of 2 minus x is going to equal 5. Well, it's isolated. So we go to step 2. The inverse. Now, with a natural log, what is the hidden base that they don't show you? E. That's a E. These two get switched places when you do the inverse. So it's now e to the power of 5 equals 2 minus x. I'm going to do a little switcheroo to make this easy to solve. Okay, rather than do multiple steps, I'm just going to rearrange this problem. I want to move the negative x to the opposite side to make it a positive x. The opposite of subtracting x is to add x. Now I'm going to add x over on the left side of the equation as well. But to get that x isolated, I'm going to now get rid of the e to the 5th. Right now it's a positive e to the 5th. What's the opposite of e? A negative e to the 5th. I'm going to move two things around at once here. So I'm going to subtract e to the 5th. Here's what's going to happen. These will simplify. These will simplify. So what is my answer going to look like? Do I need to write plus x?
No.
Just write x equals 2 minus e to the 5th power. Good. That's the exact answer. We'll go to the calculator and we are rounding to the 1,000th. Which again, 1,000 has 3 zeros, so we need 3 decimals. So this time it would be 2 minus e to the 5th. I want 3 decimals. So I'm getting negative 146.41. Would I leave it as a 3 or make it a 4? 3. That's the value I'm coming up with here. Copy this answer in. So the answer is negative 146.413. And with that, I'll let you work on your DOL. All right, the second section of solving. The second thing you need to know for solving. There is a second method of solving, and that's when you have more than one logarithm or more than one exponential. And that's what this is telling you here. Okay, there are 2 steps. I've been using method 1 all day. But if you read this slide, it tells you there's a second method, and it's called one-to-one property. That's what I'm about to walk through today. You might remember this because I actually showed you this one-to-one property when we were working on in the first half of Unit 2 on exponentials. I have shown you the one-to-one with exponentials. You just haven't seen it with logarithms yet. So now I'm just going to have both of them. So one-to-one property is what you're about to see. This is method 2. So I've taught you method 1. You're about to see method 2. And that method 2 we use if we have more than one logarithm or more than one exponential. So on example 3, what's different on example 3 from our previous problems?
3 logarithms.
We have 3 logarithms. So if you have multiple logarithms, in my opinion, the easiest way to solve is to do the one-to-one property. One-to-one means one logarithm equals one other logarithm. So I'm still not quite in good form yet. I need to make these 2 logarithms become one logarithm. We have a property to do so. What property have you learned that takes 2 logs that are adding and combines them to make a one logarithm? Product property. So this one becomes log of 2 logs adding becomes 1 log multiplying. What's 3 times 4? So on the side, I'm going to write product property. Since this is new information, I know I was not doing this on the algebra method 1 problems we've had. Example 1, example 2, I wasn't writing the properties down. I'm going to do it here just because this is new to remind you. So we have log 12 equals log of 5x minus 2. What? Let me try this again. Okay, once you have it, 1 log equals 1 other log, meaning no coefficients, nothing like that. This is in one-to-one property form. What one-to-one property states is this. If you have one logarithm set to equal one logarithm, then mathematically you can cancel the logarithms regardless of the base, as long as the base are identical. Here's what this is saying. Log 12 equals log 5x minus 2. For log 12 to equal log 5x minus 2, 5x minus 2 has to equal what amount? 12. So it's a very common sense property that if you have log of 12 equaling log of 5x minus 2, then 5x minus 2 must equal 12. That is the one-to-one property. Okay, now let's just use our basic algebra to solve from here. What would you do first to solve for x? Add 2. We're trying to isolate x. So we add 2 to both sides. 12 plus 2 is 14. 14 equals 5x. Now, divide. Because 5 is multiplying by x, the inverse operation is to divide. So we divide both sides by 5. And so x equals 14 over 5. This one, we don't have to round. We can get an exact value. 5 goes into 14 twice with the remainder of 4. You add a 0. 5 would go into 4.0.8 times. So the answer is 2.8. You can go to the calculator and get that. You could set up a long division if you wanted to, but the answer is going to be 2.8. Now I got that using method 2. Method 2 is where you incorporate one-to-one property. I want you to know you don't have to use one-to-one. What else could I have done? Is I could have subtracted this logarithm across. If I subtracted it across, I could have then applied quotient property. Do you remember that? If you're subtracting with the log, you can combine it and make it a quotient. And then you could have converted using the inverse. But I like using one-to-one. It's easier. It's, in my opinion, it's one less step. So that's why I did one-to-one. I'm going to do it again over here. What do you think we could do to solve this problem? We'll do the quotient. So this time you'll get to see the quotient if you've forgotten that. I'm going to combine these two. It says ln. What kind of logarithm says ln? Natural log. I'm going to combine these two natural logs. Whoops, that's not going to be enough space. It's going to be the natural log of, you know what? So it's not confusing. I'm going to do a square bracket first. X plus 1 times 3x minus 5. All that's going to become one natural logarithm. I didn't put the close parentheses. Sorry. Oh my goodness. What am I doing? I'm just checking to make sure you're paying attention. Let's try this again. What happens with two natural logs that are subtracting? Quotient. And so this is going to be a quotient. What goes to the numerator? X plus 1, because it's originating from a positive log. Thank you for catching me, by the way. It's about to do a lot of erroneous work. And then 3x minus 5, where does that go? Why does it go to the denominator? It's a negative log. And that's going to be equal to the natural log of 7. Now, what property was that to simplify it like that? Quotient property. 2 logs subtracting, 2 or more logs subtracting can become 1 log with a division. Okay, how do you think we could solve this? I hear cancel. Cancel what? Natural logs. Because if a natural log of x plus 1 over 3x minus 5 equals a natural log of 7, that means x plus 1 over 3x minus 5 has to equal 7. So we're going to use the one-to-one property. Which means I can simplify out these natural logs. And I'm going to drop the parentheses. I'm just going to say x plus 1 divided by 3x minus 5 equals 7. Now from here, I won't say do our algebra 1 because I don't think this would be algebra 1. Let's call it algebra 2.5. What would you do to solve this equation now? Can I do this number? Cancel, cancel.
No.
No, that would be canceling terms. Not allowed to cancel terms. You could cancel if it said x plus 1, and we could, if we could do a GCF and get x plus 1, but can't do that. So I can't cancel. What else could we do to solve? Well, if you think about this x, what is this 3x minus 5 doing to this x? It's dividing. What's the opposite of division? Opposite, or the inverse operation, is to multiply. Let's multiply each side by 3x minus 5, see what happens. If I multiply by 3x minus 5, these simplify. And so I'm left with x plus 1 equals, let's distribute. What's 7 times 3x? 21x. And then 7 times negative 5? Negative 35, good. Now I'm going to combine some like terms. Now we can combine these x's. I have an x on the left, and I have 21 x's on the right. I think it'll be easier to move the x's to the right. What's the opposite of this x right here? Negative x. Okay, since I'm moving x's to the right, how about we move the number, the constants, to the left? How do I get rid of a negative 35? Let's add 35. We are combining like terms right now. That's what we're doing, combining like terms. Those 35s simplify their opposites. These x's simplifies their opposites. 1 plus 35 is 36 equals 20x. Good. We got one step left here. To isolate this x, that 20 is multiplying. Let's divide by 20. Okay, again, you can change this to a decimal. You could leave it as a fraction. I know 4 goes into both numbers. 4 goes into 36 how many times? 9. 4 goes into 20 5 times. If you want to divide, 5 goes into 9 once with the remainder of 4. Add a 0. 5 goes into 40 8 times. The answer is 1.8. Okay, before I move on, I forgot to tell you about something. It says up top to check for extraneous solutions. You know, you might be going, what is an extraneous solution? Sometimes when you solve logarithms or exponentials, either one, you come up with an answer. No, excuse me. Sometimes when you solve exponentials, this is not true for, let me try this one more time. Sometimes when you solve logarithms, you get a value that's not true. And that's because a logarithmic domain is not all reals. Do you remember how a logarithm is not all reals? It starts with a vertical asymptote. Do you remember that from a few classes ago? Sometimes when you do the algebra, especially when you apply the one-to-one property, when it simplifies, you're going to get an x value that's not inside the domain. That's called extraneous. It means it's not a real solution. Mathematically, it looks like it should be, but it's not because it's actually outside the usable domain. So how do you check to see if this is a good answer or a bad answer? You plug it in to see, does the logarithm stay positive? Remember, a logarithm must be positive. So if I plugged in 2.8 here, what is 5 times 2.8? I'll give you a hint. We took 14 divided by 5 to get 2.8. So if I took 2.8 and multiplied it by 5, I get 14. What's 14 minus 2? 12. That's a good answer. Isn't that what it's supposed to be? That's good because it's a positive log. It's a positive number. Make sense? Check 1.8. If I plug in 1.8 here, does this stay positive? What's 1.8 plus 1?
2.8.
We're good. Come over here. What's 3 times 1.8? 5.4. What's 5.4 minus 5? 0.4. It's 0.4. Positive 0.4. We're still good. That's a good answer. When we try part C, we're about to get a bad answer. So when I start doing checking for extraneous, that's what I mean. Is sometimes we're going to get a value that's outside of the usable domain. All right, so let's begin. If you wanted to note the domain here at the start, here, what does x, remember this has to be greater than 0. If x plus 2 has to be greater than 0, x itself has to be greater than what number? If you start this way, x plus 2 has to be greater than 0. what does x itself have to be greater than? Okay, we cannot have an answer smaller than -2. Does that make sense? Check the second log. You would say x plus 3, excuse me, x minus 3 has to be greater than 0. What is this telling us? X has to be greater than 3, not 0. X has to be greater than 3. So when you combine these two, x has to be greater than -2 and x has to be greater than 3. Another way of saying it is x has to be greater than 3. We cannot have an answer smaller than 3. That's what I'm telling you at the start. So now let's just do the math. The reason I crossed this one out is because on the terms of a number line, -2, if this is 0, 1, 2, there's -2. The first answer says x has to be greater than -2 going this way. Does that make sense? The second value says x has to be greater than 3. The only one that works for both is values greater than 3. It cannot be in there because it's not true for that logarithm. So our answer has to be greater than 3, if that makes sense. Okay, let's solve. What can I do with two logs that are adding? I'm going to multiply. So this is going to become log 3. And here I'm going to do that square bracket because I'm going to multiply x plus 2 times x minus 3. And that will equal log base 3 of 14. Now I know at this stage you might be wanting to zone out. Please don't. Stay locked in here. What property did we just do there in purple?
Quotient.
Not quotient. This one was product. Now to simplify this problem, I have one log equaling another log. What property could I do now? What's it called when you cancel the logs? We're going to do one-to-one property. We're going to say, now I'll drop those square brackets, x plus 2 times x minus 3 has to equal 14. I'm going to distribute this. A lot of students or a lot of people call this foiling. When you multiply, you need to super distribute. Everything gets multiplied by everything else. What's x times x?
X squared.
X squared, that's x times x. The x also needs to multiply times -3, which is -3x. 2 will multiply times x. And 2 will also multiply times -3. -6. And that will equal 14. Now flashback to unit 1. First few lessons we were solving with polynomials. If your power is greater than 1, the way to solve is you use the zero product property after setting it equal to 0. So that means factoring. Big word just to say factoring. Let's set this equal to 0. How do I get rid of this 14 here?
Minus.
I'm going to subtract 14. So I will have x squared. I can combine these two terms right here. I have a -3x plus 2x becomes -x. And then I have this -6 minus 14 more. And all that equals 0. So now what I'm going to do is I'm going to factor. The reason I factor is I can use zero product property to get my answer. So I'm going to use, since this is a trinomial, well, rather than me tell you, do you remember what to do if it's a trinomial? What type of factoring? Let's do X method. We do factors of a times c in the top of the x, b goes down at the bottom of the x. What is 1 times -20? -20, and b is, you're thinking of numbers that multiply. I'm going to deal with just positives for a second. Numbers that multiply to be a 20, but somehow combine to be, or have a difference of 1. 4 and 5. It's not 1 and 10. I mean, excuse me, 1 and 20. It's not 2 and 10. So the only other option is 4 and 5. Those are 1 apart. What makes it be a -1?
-5.
Now check it. Is 4 times -5 and -20? Yeah, so it takes care of both. If you remember, you split this power because we were multiplying now. So instead of x squared, it's x times, in one parenthesis, times x and another parenthesis. That gives me the x squared. Adding in +4 and -5 make up the -x minus 20. Set that equal to 0. Now, according to the zero product property, that's an algebra 2 property. You also saw it in unit 1 that states if you are multiplying, meaning you have a product and the product is 0, what's the only way to multiply and get 0? You have to multiply by 0. So what would x equal in this first parenthesis? X equals -4, or x equals, in this parentheses,
+5.
5. Now, this is the problem where one's good and one's bad. Remember up top we said using the number line, both these two answers are not filling in on the shared interval. Is -4 on that interval?
No.
No, -4 is going to be what we call extraneous. So -4 does not count as a real answer. Here, I want you to put that this is extraneous. Do not count it. So I'm going to mark it out and say extraneous. It is not a real solution. X equals 5 is your only true solution.
At the beginning, why was x is greater than -2 and 1?
Because a logarithm, rule number 3, if you look over on the domain rules, a logarithm, it says on my rule number 3, you cannot take a logarithm of a non-positive number. That's another way of saying logs must be positive. And so what we did is we said x plus 2 has to be greater than 0, meaning positive.
What if both of them,
And so
what if both of them were greater than 0? Like what if instead of
then we'd have multiple answers. If this was x equals +4 and x equals +5, then they both would have been solutions. Yep. All right. Now that's a lot to take in. Do you want me to work the next one and then go to graphing for both of them, or go to the graph now just to rest your hand for a second? Which one's better? How about we go to the graph now? I'll just prove it to you real quick. What I'm going to do is open a new document, and I'm going to show you these two graphs side by side. I'm going to graph log base 3 of x plus 2. X, where's x? Oh my goodness, x plus 2. And this is adding log base 3 of x minus 3. And what I'm going to compare that to is this as a second equation, the log base 3 of 14, log base 3 of 14. I want to compare it to that, and I want to see where do these intersect. Now, as I go full screen here, you will see there's only one intersection between these two logarithms. Why did that not move? Let me try that again. Move. There we go. There's only one place these logs intersect one another. If I press menu and choose analyze, I can determine that the only place these two graphs intersect each other is at what x value. And that's what we were solving for. We were solving for x. We weren't solving for y anywhere. We were solving for x. What did we get? 5. If you're wondering what's the 2.4, that is what log base 3 of 14 is. That right there is a constant. There is no variable. That's a constant. That is the 2.14. That would be your solution there. So that's confirming what we just established. Was -4 an answer? No, because this logarithm did not get graphed. It was outside the domain. And so that's why that would be the answer. Let me go ahead and add this picture in over here. I don't know where to even put this, but I'll put it right down there, and you can see that that's a solution. All right, let's reload and do this one more time. Okay, part D. To combine these, can I combine these two logarithms right now? No, I have to perform something first. I can't divide the 3 either because I'd have to distribute the division. What could I do with the 3? Power property. We're going to do the power property first, which states that this will be log base 4 of x minus log base 4 of, I could write it as 2 cubed. Do y'all know what 2 cubed is? 8. I'm just going to write it as 8 equals log 4 base 4 of x plus 7. Now what?
Product portion.
Quotient property. 2 logs subtracting can become 1 log dividing. So this logarithm here should now look like log, what? There we go. Log base 4 of, what's the way we normally, oh wait, that's division. I'm sorry, I almost did it again. It's division. So what goes to the numerator? X, because it originates from a positive log. The 8 coming from a negative log goes to the denominator. And that will equal log base 4 of x plus 7. Now what can we do? If it's 1 log equaling another log, we can apply the 1-to-1 property. 1-to-1 property. Which means we have x plus x divided by 8 has to equal x plus 7. How do y'all want to solve that? Okay, we can multiply both sides by 8. So I have x equals, let's distribute here. 8 times x is 8x. 8 times 7 is 56. Let's combine some like terms. I'll subtract the 8x across. X minus 8x is, no, it's a positive 1 minus 8 is negative 7x equals 56. And last step, divide by negative 7. We'll divide by negative 7. That's multiplying there. So I divide by negative 7. And what do we get as our solution here? Negative 8. Now, before I circle it up, say it's final, let's go up here and check our domain. This, according to this logarithm here, if we did our domain here, what does x have to be greater than if it's just by itself? Log must be positive. X has to be greater than 0. Or over here, x plus 7 has to be greater than 0. So if you solve this logarithm, you would subtract 7 from both sides. I'm sorry, if you solve that inequality, and x has to be greater than negative 7, or x has to be greater than 0. Let's number line this. Here's 0. 1, 2, 3, 4, 5, 6, 7. Here's negative 7. One inequality is saying you have to be greater than negative 7. The other inequality is saying you have to be greater than 0. What's the only one that overlaps both? Is that we have to be greater than 0. We have to be a positive number. Is that positive? No. So what do we say about this? Extraneous. Do we have any real solution? No real solution. And again, I could demonstrate by graphing that won't intersect it. So you could graph the two sides and you'll see they never intersect one another. There's not a real solution. All right, I have a couple for you to practice. All right, moving along. Example 4. It says let f of x equal the natural log of x plus 10 and minus natural log of x, and g of x equals natural log of x. Find all values where the graphs of f and g intersect. So now we're going to go look at the graphs here. So now we're going to look at the graphs. So I'm going to open up my Inspire. Let me get it to where I can graph easier. And what we're going to do is graph these as two different equations. We have the natural log of x plus 10, which, by the way, this will say if it's x plus 10 that our x has to be greater than negative 10 minus the natural log of, natural log of x, which this would say x is greater than 0. So we have to be greater than 0 because that's the number more to the right. That's our first graph. And notice it is just to the right of 0. That's all it is. And then we also have a second graph of natural log of x plus 3. This will be all values where x is greater than negative 3. Hit enter. How many solutions do you see here? Okay, so let's find the solution here. I'm going to analyze the graphs. Notice they only intersect in one place. That's what I'm looking for, intersection. Go to, this is telling the calculator where to look. Lower bound means look below, to the left of. Upper bound means to the right of. This is the answer here. The solution is actually the x value. So that would be our solution there. Tools, screen capture. So let's come back over here. So we want to find all values where x, the graphs of f and g intersect. What's the answer going to be? What's the only x value? 2.32. And I'm assuming that's rounded, so I'm just going to do approximately 2.32. That is the only value. Now, just as a reminder, the domain, this was cut off at 0 because of this natural log. This graph started from values greater than negative 3 because of this natural log. Great, so you have a DOL here where you can do the same. Look at your graph and go on from there. All right, last thing we're going to look at is inequalities. I'm jumping ahead of myself. Let's practice doing some inverses here, and then we'll do inequalities. Okay, so finding the inverses first. We will get to the inequalities here. Let's find some inverses first. And remember, inverse means we need to switch x and y. So f of x is represented here by y. So the first thing to do would be to exchange x and y. That's step one when solving an inverse, is you switch your x and y, and then from here you solve for y. Okay, so if I wanted to solve for this y, to isolate this y, I need to first get rid of this negative 15. So I'm going to add 15 to both sides. Okay, so I'm left with x plus 15 equals 3 times 2 to the power of y minus y plus 4, sorry. And here, what I will do now to isolate this 2, now I can't multiply this 3 times 2 because the 2 has a power. So that would be breaking PEMDAS. 2's got to be raised to the power before it can be multiplied by 3. So the other thing I could do is the opposite of multiplying by 3, which is dividing by 3. So I'll divide both sides by 3. And so now I have, and you could simplify this. I won't, just because I want to talk through inverses, and I think it'll make it look better if I do not reduce this. So I'm going to leave it like that. Equals 2 to the power of y plus 4. Now that I have this isolated in an exponential form, what I will do is to get this y isolated, as I have to change it from exponential to logarithmic. So that's what I'm going to do here. Let me come up, and so I have more space. I'll write right here. I'm going to change it to log with a base of 2, and I'm now going to apply the inverse here. So since I'm changing it to a log, which is inverse, I need to switch these places around. So it's log base 2 of x plus 15 all divided by 3 equals y plus 4. And then mathematically, you only have one step left to get y isolated. We need to subtract 4 from both sides. To isolate this y, I subtract 4. Now that I have y isolated, I'm going to write the answer in inverse notation, which means f negative 1 of x. And this should be a function because a logarithm is a function. So it'll be log base 2 of x plus 15 divided by 3 minus 4. Now that's my answer there, and I want to remind you on the domain, this would have to be greater than 0. This inside would have to be greater than 0. So if you wanted to write the domain here, x plus 15 would have to be divided by 3 would have to be greater than 0. So you could work through and solve this. But you'd find out first we would need to multiply it by 3. And then you would add, so what is 0 times 3? Well, that's still 0. So you don't even need that. That cancels. And then I would subtract 15. I would next subtract 15. So it'd be 0 minus 15 is the domain, which means if I wanted to simplify all this, that our domain is x is greater than negative 15. So just to make it clean, I'm going to go ahead and erase this and redraw it here. X has to be greater than negative 15. That would be your domain. If you need to know that, x is greater than negative 15. Again, because this has to be greater than 0. Okay, so there's all my answer to part A of the finding the inverse. Now, why did I want to write it in the form I did? I was mentioning because I want you to look at transformations. Notice this is a vertical translation down 15 on the y-axis. So over here, this would appear to be, since it's a liar, not plus 15, but minus 15 on the x-axis. Now, what's different is this here gets vertically stretched by 3. Here, I would have a horizontal dilation. And again, since it looks like division, it would actually get multiplied by 3. So notice that would occur. Instead of going left, because again, x is liar, instead of x is going left, the y's go down 4. So instead of going left 4, negative 4 on the x-axis, you go down 4 on the y-axis. So they are inverses. That's how it works. This would be the range over here. If you were to graph this, usually exponentials follow the x-axis, but because they're shifted down 15, this will be all values greater than 15. And so that's the range, y values. Over here would be domain. And so those are inverses one another. You could graph them and see that this is the same as this equation once reflected on the line y equals x. Okay, I'm talking too much. Let's just go look at the next problem. I'm going to slide this over, give myself a little bit more room to work. Let's just slide this. Oh no, that's not what I want to do. Slide it over this way. And now let's work here. So if I want to do the inverse one more time, I would switch x and y. So this is my y. That's my x. I'm going to switch x and y. So we'll say x equals negative 3 log base 5 of y minus 4 plus 6. Okay, what do I do first? Well, let's subtract the 6 to isolate this logarithm. Note here that the original domain is that x is greater than 4. The logarithms, the range is all reals. The range is all reals. Double R. There we go. Now I subtract 6. I'll come back to this at the end. So we have x minus 6 equals negative 3 log base 5 of y minus 4. Okay, now this negative 3 is multiplying the logarithm. You could raise that as a power, but that doesn't actually simplify anything. If I wanted to simplify, the opposite or the inverse operation of multiplication is division. So I'll divide both sides by negative 3. And so I have x minus 6 over negative 3 equals log base 5 of y minus 4. Now that I have this logarithm isolated, I can apply the inverse here. To drop the logarithm, I'm going to apply the inverse. So these two will switch. And so we'll say this is 5, not raised to the y minus 4. It's now raised to all this. Let's see, x minus 6 over negative 3. And that will equal y minus 4. So the last step to get my answer is I'm going to add 4 to both sides. Now this adding of 4 needs to be on the outside. So now I'll write my answer over here. Since this was g of x, I'm going to rewrite this as g negative 1. That's inverse notation. Would equal 5 to the power of x minus 6 divided by negative 3. Goodness gracious. -3. And then the +4 on the outside, +4. And this domain will be all reals because it's exponential. Exponentials have all reals as their domain. When originally this was the range. So that right there would be our solution. That is our inverse. And I want you to compare real quickly. This has a vertical translation up 4. Over here, this was saying right 4. Oh, that domain was not right. You would have to add 4, so I should have. Goodness, should have had that as x is greater than 4. The x values would have to be greater than 4 for this logarithm to exist, which means that would be our range over here. Our range would now be that y is greater than 4. Over here we went, this is on the outside, so up 6. Over here it looks like to the right 6. This had a vertical dilation of -3. Now we're vertical dilation. It looks like dividing -3, but remember that's going to be the opposite. So instead we will multiply by -3. And so as you work through it, you'll notice that those are inverses of one another, and that's how inverses work. Okay, you switch x and y, so what was vertical becomes horizontal and vice versa. Domain, range, everything changes. With all that, you can now work on your DOL here. Oh, yours is a little bit different. I'm reading this. Let h equal this, k equal its inverse. What values of x does k equals 1? That means the inverse. So if this is the inverse, then that's in the place of y. I'll give you that hint. K of x, that represents the y. So if y equals 1, now that's coming from the inverse, then that would actually mean that, I'll let you solve that. What does that actually mean about this equation? If it's the inverse, if on the inverse, the y equals 1, what does that mean about the original? I'll let you use that to solve. All right, let's finish up this lesson. We're going to go to example 6. What we're going to now do is find the solution to each inequality, and I'm going to use graphing technique. I have a different video you can look up if you want to see the algebra. But what I'm going to do is using graphing here. And it says to restrict the domain on each. I will do that by hand first, kind of give you an idea. Remember, a logarithm must be positive. So what the easy way of thinking about this is this logarithm that x plus 3 has to be greater than 0, which we can state then confidently if I subtract 3 that x has to be greater than -3. So on a number line, these are going to later be critical values. If that's at 0, let's just say it's 0. If I go 1, 2, 3 to the left, what I'm saying about this is that I have to have values that are greater than -3. There's -3. I have to have values greater than -3. Over here, if you think on this, this is a parabola. I want you to think for a second on the inside. It's a parabola. If you remember, the shift is the inside. It's the, if you remember from algebra 2, it's the opposite of b divided by 2. So instead of being -4, it's going to be +4 divided by 2, which is +2. You're shifting right 2, but then you have to hit that +7. That won't ever have a negative value. Because if you're shifting right 2 units and you're up 7 when you hit there, you're at 7. The values, there's a x is 2 different value. You would square that. So 2, since I'm 2 units this way, 2 squared is 4. The vertex will be 4 units minus 7. What's 7 minus 4? Well, 7 minus 4 is 3. The vertex of this parabola is positive. This parabola will never be negative. Therefore, this logarithm will never be negative. This domain will be all reals on this logarithm. I'll show you graphically that in a second. I want to know where this is greater than 0. So you can do the algebra, but let's just go through the graph here, and let's see here. I'm going to graph. We want to know where this equation is greater than 0. So graph, I have a logarithm of, it's a common logarithm, so base is going to be 10. X squared, x squared minus 4x plus 7 minus log of x plus 3. And I want to know where is this greater than 0. What I could do here is I could zoom in and I could give you all the values here. Let me make sure I type this in right. I did not. I was gonna say, I thought the answer is gonna be a little different than that. Like there we go. We want to know, where is this greater than 0? Well, to help me out, I'm going to analyze this graph and find the two spots where it hits the 0, which you can kind of see in this picture, but just in case you can't, I have a 0 here. And I have another 0. Come on now. And another 0 there. There's my two zeros. So I'm going to take a picture of this. And I'm going to include this. Here's going to be my solution. So I can see this. This has a vertical asymptote, just like I told you would, at -3. So remember how I said the graph has to be greater than -3? That's the vertical asymptote I just added right there. X equals -3. This picture is only on the right of it. It's only the values greater than -3. Let me make this go a little thinner here. So you can see it's only the values greater than -3. This graph is above 0 from -3 until 1, and then from 4 to positive infinity. And so that's what the solution set's going to be here. The solution set would be parentheses, because you cannot be equal to a vertical asymptote, from -3 up until positive 1. And because this has to be greater than 0, that's where it equals 0. So it's a parenthesis, not a bracket. Union, I have a break. This is not a part of the solution. So it goes from 4 to infinity. From 4 to infinity. Again, I'm using a parenthesis, not a bracket, because I cannot be equal to 0. It'd be different if you had that symbol, then these two would be brackets. You would include the 1 and the 4, but we don't have that. Now, again, you can, you know what, I might do this really fast for you, but you could go online and watch this where I go through a lot slower, the algebra. What I'm going to do here, 2 logs subtracting is the same thing using the quotient property. I'll just do QP. I'm going to do this real fast. What you would do is you would divide that. So log of x squared minus 4x plus 7 over x plus 3 would have to be greater than, that's the quotient property. That has to be greater than, oh no, plus 7 x plus 3. This has to be greater than 0. Now, if you want to convert, how you convert with an inequality is the hidden base here is 10. When I apply the inverse, the inequality stays pointing at the x. So I'm going to have 10 raised to the 0. And the inequality is going to point at the x's. So it's going to go this way, because these two switch here when I apply the inverse. These two switch. And so x squared minus 4x plus 7 over x plus 3. Now, if you don't know 10 to the 0, that's actually 1. So how I'm going to solve from here is I would multiply by x plus 3. X plus 3 would multiply 10 times 0. Now 10 times 0, that is 1. That right there is equal to 1. So I have x plus 3 is less than x squared minus 4x plus 7. I'm doing the algebra here. I'm going to set this equal to 0. I'm going to have to subtract 3. And I'm also going to subtract x here. Okay, I'm trying to go as quick as I can and still showing you the algebra. You can slow it down, look at it. Now, the reason I'm doing this is because I need to use zero product property. Combining like terms, negative 4x minus 1 more x is negative 5x. 7 minus 3 is positive 4. Positive 4. And so now I would do, this is a parabola. Again, I want to know, where is this greater than 0? If you factored this, do A, B, C, factors of 4 that are greater than B, negative 5. Well, the factors of 4 are 2 and 2 and 1 and 4. The only ones that can give me 5 is 1 and 4. To give you a negative 5, they both have to be negative, and negative times negative is positive 4. That's good. So 0 is less than x minus 1 times x minus 4. If you just think graphically, this is going to be the easiest way to solve this. Graphically, we want to know, where is that greater than 0? So rather than doing the zero product property, that would tell you you hit the x-axis at +1 and +4. 1, 2, 3, 4 on the x-axis there, y-axis. Because this is a positive parabola, you hit on these two spots and it goes this way. We want to know the values where you are greater than 0. Well, from the left, and then from the at the right from 4. So why isn't it left forever? Because we had this vertical asymptote. Remember, x has to be greater than, we found out at the very start, -3. So 1, 2, 3. If I added in that same vertical asymptote there, you would say, okay, this area in here is a good answer because that's going to be greater than 0. All this area, and then this area of the graph going this way. So this is from -3 to 1 union, because that's below 0, it's less than 0, and then from 4 to infinity. And again, the cutoff is from the domain right there. That's how you do it by hand. That's a lot. I get it. That's a lot. That's why I said it's easier to graph it. But those would be the critical points coming from here. So let me put that on here. The critical points would be solving this as if it were an equal sign. That would be the x equals 1, 4, and the asymptote up there, -3. Those would be the values that you'd be checking with. You can be plugging in numbers if you wanted to, anything to the left, to the right of -3, left and right of 1, left and right of 4, to figure out your values. Those are the critical points you'd be testing. Okay, let's try part B again. So one more time, I'm going to use an equation. I'm going to use the graph first. We want to know where g is less than h. Okay, so let's go look at our graphs here. Equation g is going to be f1. So it's going to be the natural log of x squared plus x minus 5. And then our h is going to be the natural log of x plus 4. All right, now I'm going to go add some values. We want to know where that's g is either less than or greater than h, I forget, but I'm going to write it like that. What I'm going to do is analyze this graph and find the intersections of these two graphs. So here's an intersection, and menu, analyze, intersection over here. These are the values where they cross each other. Okay, I'm going to take that and we're going to go get our solution from here. Okay, and I'm going to add something in as well. On the red graph, there is an asymptote here. You can look off of there. This is saying x values have to be greater than -4. So if you look at this graph, this is -1, 2, 3, 4. There should be a vertical asymptote. And so we wouldn't even consider the values to the left of -4 because that's outside of h's domain. So we're only going to be looking, so -4 is going to be like a critical value. We're only going to be looking to the right of this. Now in the blue, what's weird is it's two separate logarithms. Notice they're both approaching asymptotes. So we're only going to be looking on the outsides of these two asymptotes. And I'm going to do these two in blue. Blue. Here. And here. Now you don't know what those values are yet. So we're only looking in between this window, not over here. So this is outside of, let me go ahead and write a note that h is red here. H is graph, this is h here. H is red, whereas g is blue. Now this section over here is outside of h's domain. So there's no red graph over here, so that won't be part of the solution set. And in here, this is outside of the blue graph's domain. So this is outside of g's domain. Does that make sense? So we're only looking in this window and this window. And as you can see, we want to know where G is less than H, meaning where blue is lower than red. Where is blue lower than red? Not here, but over here. This little part is a solution set. So right in here, this little sliver, that's going to be an answer set. And where's blue? And this little solution set. Now that's where the solution will be, which is difficult to find out with technology. But here's the algebra as quick as I can. I want G of X, the natural log of X squared plus X minus 5 to be less than H of X, which is the natural log of X plus 4. Well, I can do one-to-one property. I'm doing one-to-one property and say that X squared plus X minus 5 has to be less than X plus 4. Doing my algebra, I would subtract X from both sides, and I'm going to subtract 4. And so I find out that X squared minus 9 has to be less than 0. This is again a parabola. And if you think about this parabola, this is shifted down 9. You can do difference of squares, and you'll get that X minus 3 times X plus 3 is less than 0. Or you could have just said, okay, that's a parabola, and it's down 9. Down 1, 2, 3, 4, 5, 6, 7, 8, 9. You're down there. That's going to get really ugly. Let me just do it like this. I'm going to put that there and say that's down 9. But now, according to this, we're the first one's this one means right 3. This means left 3 because X is a liar. That's where our parabola goes through. We want to know, where is this parabola below 0? Well, it's below 0 in this range. So you would think that's the answer, but because of our domain restrictions, remember we stated earlier that we have to be greater than -4. So starting at -4, you would cut off the graph. You wouldn't look anywhere. So I'm going to, instead of doing an arrow there, I'm going to take that up and do like an open circle. That graph gets cut off right there. And then this cuts off part of your graph as well. This domain, this has to be greater than 0. Now the problem is X squared plus X minus 5 has to be greater than 0. That's not easy to solve because if you do X method, it's not rational. So what are factors of -5 that add up to 1? It's not rational. Now I know a shortcut. You probably don't know this shortcut, but that was what you do is you take your b and divide it by 2. So it's 1/2. And it's going to be plus some number and minus some number that when you multiply it, some square root, I should say, that you get -5. So mathematically, it looks like this: 1/2 times 1/2, which is 1/4. The 1/2 would multiply this square root, and this square root would multiply this 1/2. And notice those would cancel because they're conjugates. That's a -half of square root, +half of square root. Those would cancel out. But then you would multiply, and you'd have a negative times a positive of a square root squared, which that will cancel out, equaling -5. And so basically you're asking yourself, since these cancel out, 1/4 minus what amount is a -5? Well, 1/4 is 0.25. So 0.25 minus what amount is -5? You can subtract that 0.25 and you'll get it's -5.25. Now I'm going to change that to a fraction. So I could say 1/4 minus 21/4. Maybe that's the easier way of writing it, is -5. 1/4, that would be 20/4. Let me write it this way. 5 is the same thing as -5 is the same thing as -20 divided by 4. Notice that mathematically works. So that's the value that goes inside this square root. It would be 21/4, 21/4, 21/4. Now, what does that mean for you? Oh my goodness, what does that mean? That domain, let me just write it over here. That G's domain, here, G of X domain. Here's what that means: that X plus 1/2 plus the square root of 21/4 times X plus 1/2 minus the square root of 21/4 has to be greater than 0. And so again, graphing this, what you'll find since that's a positive parabola, since that is a positive parabola, remember we're getting it from right here. This x squared plus x minus 5 is greater than 0. Because that's a positive parabola, you would be looking at only the window, positive parabola. Now we can get our roots here. This would be -1/2 minus the square root. I'm just going to put it over here. That's -1/2 minus the square root, and I'll reduce this 21 over 2. You know what, I'll write it like this. Negative, how about fraction? 2's on the bottom, negative. That is, because inside lies, so -1 minus square root 21. And you would also have -1 plus square root 21 over 2. So it'll be a positive number. I'm just going to put it over here. -1 plus square root 21 over 2. You would only be looking for the values that are greater. So you're looking on the outside of there. So this is the craziest problem to do ever. This part would not exist on the domain. Remember, this part would not exist on the domain because you'd have to be greater than 0. So you're looking outside of those values. So now coming back over here, this means we have an asymptote at that value and an asymptote at that value. Mathematically, that's right there. So I'm going to go ahead and add this in. That right there is x equals this value, -1 minus square root 21 over 2. That's that value right there. This asymptote is x equals -1 plus square root 21 over 2. And so now we can finally write down our solution set. The solution set to this problem is the longest problem ever. Where am I? That's not it. I want the blue to be below the red. From this point, from -3, here until this line, which is -1 minus square root 21 over 2, union. And then over here, blue is also underneath red. From this point, -1. Now it's a plus square root of 21 over 2, comma, up until that point, which is at 3. That's your solution set. Goodness, that's crazy. There's your solution set. And what else was I going to mention in there? I've already forgotten what I was going to say. Must not have been that important. Yeah, that's the solution set. It's from in that area in there. So yeah, that's a lot of problem right there. I don't even know where to begin or end with all that, but that's how you would do that. That is a lot of work. So good luck. That takes you to your DOL. I'll let you work through this one. This one, I promise, is a little bit easier to solve.